Okay. All right. So this is like this is now our entrance into supervised learning. So I think the things that we've been doing before are considered unsupervised, and these are supervised learning. And so I guess we'll talk about a little bit of what supervised learning means, and then we'll talk about linear regression. And then I guess there's some extension to linear regression. So my understanding of supervised learning is that you have some function that you are trying to you have some function that you basically assume the data is going to take, and you have some training data that will allow you to basically get a fit of the parameters in your function. So you basically have like some you basically have some understanding of what this function is going to look like, and you have some data, and then you're trying to find the parameters of that function. So these functions could be linear functions, right? And that's primarily what we're going to talk about today. But there's also like other types of functions where they're not linear, they're parabolic, or whatever. They have some other shape. But basically, you're fitting some data onto that function, and then you can use your new data. So here you have training data. You have the x and the y. So you have like basically the input and the output, and you use that to find the parameters of your function. And then now you can use just the input to predict the output after you've decided the parameters, after you've learned the parameters of that function. And so there's two types of tasks with this. One is and move this out of the way. One is regression, and one is classification. So when the function is continuous, you're doing regression, and when it's discrete, you're doing classification. So we won't get into classification, I don't think, until like the last of these lectures, but we'll talk about that in this lecture, or in this time. So for example, as an example of supervised classification problems, you start with training data, for example, 6,000 examples of each digit. And apparently I guess the state of the art can achieve testing error of 0.4%. And this is one of the first commercially and widely used ML systems.
That's so cool.
Yeah. Another example is rent prediction. So suppose you want to move to Atlanta and you want to find the most reasonably priced apartment satisfying your needs. So this is, I think, more of continuous regression. So this is a regression problem. So you have some data, some training data that you have, how many square foot the place is, how many number of bedrooms, and then the rent. And you also have some test data of these two parameters, or these two features, living area and number of bedrooms, and then you want to find out what the rent should be, or I guess how much you would pay, for example. Another example is stock price prediction. So you can kind of collect some features about the stock and try to predict the stock price at a future date. And then this is another classification example. I guess we just kind of talked about it, but you have some digits, and the features are the pixels in each image. So you have some vector of features that are 784 dimensions, and the goal is to learn the classifier f of x such that whenever you give the input x, which is the pixels, you get out one of these digits. So it can just basically say, okay, this is the digit. And then there's another example, spam detection. which is used,
Oh,
classification is used to do that. So task is to classify email into spam and not spam. The data is where it can be, I guess this seems a little too simple to me for the data to just be word count.
okay.
But it requires learning system as enemy and keeps innovating. So I guess this is something that like also takes into account or can take into account your input
Yeah.
as a user. So yeah. Okay. So this is, I guess this kind of goes back to that example of the rent. So you have the features, learning, living area, distance to campus, number of bedrooms, etc. And you denote these features as X. And so that's what we're going to use for the rest of the time here. It's just denoting the features as X. And then the output, which is the rent, we're going to denote as Y. And so you define some training set where you've collected data. Maybe you've called some renters, and you basically get some data about what the rent's gonna be. So this is a little bit confusing in this case because these are actually, so when we say n, each of these x1, x2, so it's kind of misusing notation, but each of this x1, x2 is d-dimensional, but these are the individual data. So x1 is d-dimensional, x2 is d-dimensional, and so on. So you can plot that rent versus living area, or you can plot it and to do a linear regression there, or you can do a linear regression on multiple features. So you have living area and location, and you have some sort of plane that represents the data, the training data, or your function, I guess, the plane that represents your function. Okay, and so this is the problem setup. So you have some set of n observations, your training set, and so you have the features, and you have the output or the targets, and the regression problem is kind of repeating a lot of the same stuff, but estimate yx from this data. Okay, so now we'll talk about linear regression. I guess this is funny. Okay. Yeah, so I guess this is kind of like showing what we just showed up there. So if you have just like one feature, then you just literally have a line with some kind of your standard mx plus b. But you can also have linear regression where you have multiple features and you're fitting sort of like a plane across multiple features. So here is here's the standard form. So you have your features x1 all the way to xd, and you have some parameters theta 1 all the way to theta d, or I guess theta 0 all the way to theta d. So this theta 0 is considered like a bias, kind of like your what is it? Your slope, your y-intercept or something like that. Yeah. And usually, you know, people will write this standard problem with some noise. I think we're going to ignore that in this lecture, but you can also think about it with some noise, and then there's like yeah, there's like other really cool things that you can do in linear algebra to like sort of yeah, sort of get a model for the noise, and then use that model to kind of fit, use that model for the noise to do your linear regression. But I think that's beyond the scope of what we're going to be doing here, but there's some more stuff that you can do here. Okay, but the way we do it is just to find the least. So we call these least squares in my field, but I guess least mean squares is what the computer scientists call it. And basically, you're looking for the parameters, or basically the coefficients, right? The coefficients of this line, or this linear combination, that's going to minimize this objective function, and the objective function is the observed output minus the I guess observed feature.
What up? Your sound went bad again.
Yeah, so you take the error between those and you square it, so you don't have like the negative or positive, and so you're just looking at like a you're just looking at some number, right? Some positive number.
Some distance, essentially.
Yeah, some distance. So yeah, I mean, this is pretty basic. So you have this function that you're trying to optimize, and so you could just take a gradient of this, right? So you could take so this, I guess we're considering this to be just one line. So considering this to just be one parameter here. Are we doing that? Yeah, I guess so, because this is just one theta. So yeah, assume for now just this is one theta, and then we'll sort of expand it to more parameters. But yeah, so you take the gradient or the partial derivative of the loss function with respect to that parameter, and the math turns out to be this. You set that equal to 0. And then you can kind of rearrange that by multiplying out this this function in here, and so you have your xit. And remember, these are vectors, so this xit is some vector and yi is some vector. And then you have the same thing here, or I guess y could be a vector, or could be just one feature, or one output. And then you have the same thing here: xit xi times theta equals 0. And so in matrix form, if you have all these features, then you can write your xi, and this is important to note. Since we have that bias term that we're going to, this theta 0, this bias parameter, we have to append the x data that you collected with a 1 at each one of these data points. So this top part, or this first row, is like one of your data points, and it's d-dimensional, so you can see the 1 through the d, and you have to append it with 1 so that when you multiply it by theta, the right multiplication comes out. So you have your bias term, and then you have your sort of collected y data as well. And so this is showing the matrix multiplication here. So we're basically just taking this this sum form and putting it in matrix form. So you can see that it's the same. You're going to get the same sum as if you did just the summation form. And so now we can write that. Now we can write this L in matrix form as this here, where it's just y minus x theta transpose times y minus x theta. And you'll get the same form. So now we let's see. Okay, so this is the form that we had before. Set it equal to 0, the gradient that we had before, and so we can take the gradient again, and this time we just write it in matrix form. So we have some x transpose y, which is this part, x transpose y, and then x transpose xi, this part. And so you can see we're now labeling these x transpose and x. And so we define x as this vector, y as this vector. We did that in the previous slide. So we can write this matrix equation in this form, and then we can just move things around, right? So we can first factor out this 2n, 2 over n, and that ends up canceling. So we basically just have this x transpose y plus negative x transpose y plus x transpose x equals 0. Shuffle things around, and we'll get X transpose X equals X transpose Y, or I guess theta, sorry, theta. And if we want to solve for theta, then we just take the inverse of that matrix, X transpose on both sides. Inverse times X transpose times Y. Right, so that's what they have here. So this is a pretty standard form from least squares, and you'll sometimes hear it called the normal equations. But yeah, so you just take the pseudo inverse, and this is a pretty common command. You can type in pnv in MATLAB, and it'll be it'll compute that for you. And so yeah, it's a pretty standard command.
Can
Yeah.
you just real quickly, how did this derivation connect to the previous one? It seems like
Which
I'm just
previous one?
connection.
This one?
Yeah, so we went to here, and then we broke it into matrix form,
Mm-hmm.
and then we went back to the equation for the, I guess.
Yeah, so this is the same equation as this equation, right?
Yeah.
I think they just, in order to prevent you from having to go between slides, they just rewrote that same equation at the top, knowing that you're about to go into matrix form. I don't think anything different happened.
Oh, so it's the same thing, but we just wanted to break it out and make it explicitly matrix form so we can
Right.
matrix functions.
Mm-hmm.
Okay.
And then they're showing you that the matrix form, each like, never mind.
Okay.
Yeah, so this is basically what Ban's doing with this code. Like you can write things as summation, which is going to take so much longer to compute than if you, because a lot of these systems are, or a lot of these languages are optimized for matrices, so it's easier to just write it in a matrix form. It's also easier to communicate because you have to write less things.
Mm-hmm.
Okay, so now we've established that this is how you find these optimal parameters that minimize your loss function, defined as the mean square error. Okay. And so there's let's see what this says. So this d by d, which is going to be the, what are we doing here? Okay, this is X transpose X, gives you a d by d matrix, not a big matrix because n is much greater than d. This matrix is invertible most of the times. If we're very unlucky, the columns of X transpose X are not linearly independent, and then it is not invertible. Okay. Yeah, I mean, so you don't really need to worry about this because you can always just do the pseudo inverse in MATLAB, in whatever program you're working on. And if this actually is invertible, then it'll just take the inverse of it. But if it's not, then it'll do the pseudo inverse. So don't worry about that.
Okay, nice.
But there is another way to optimize that'll be useful in the next lecture when we don't have closed form solutions like this. And so this is a nice way to using the closed form solution, or not using the closed form solution, using that something we already have the answer to kind of talk about gradient descent is a nice way to visualize it before you kind of go into stuff that doesn't have a closed form. So yeah, so something that you will see that it's is that sometimes this computation, this inverse, can be very expensive to compute. It's actually something I deal with a lot in my research, and how to like make this easier to compute for optimizing trajectories for 3D printers and stuff like that. But yeah, so we talked about how this is the gradient of the loss function. And so so gradient basically defines the direction where when you move, let's see, yeah, the direction where you would get the most how do you-
It'd probably be the direction that you're moving in the direction with the least amount of change. Like you want to
isn't it the
minimize.
most amount of change?
I think it's the most, right?
Yeah.
It's like the
Yeah,
steep part of the slope. If you look, if it was like topographical.
Yeah.
So
So the gradient defines that, and so basically you want to move in the direction that gets you sort of the most bang for your buck, right? And so this is the same as this, right? From the derivation of the gradient, and basically we're going to take a step in the direction. So you assume that you have some theta that you start from, some parameters that you are starting from, and then you just basically continue to take steps in the gradient direction until you can sort of converge on a point that like doesn't sort of change anymore, right? So this alpha is defined as the step size. So that you can choose, and there's probably ways to choose that. And so instead of having this 2, you just plug in this alpha, and you get to sort of choose the way you take the steps. But yeah, so basically it's the same thing. You take a step in the direction of the most change, and then you can try to see if that beats, the time it takes to compute this function here.
okay, let me make sure I understood what happened here. So when you say it converges, you're saying that you're going to keep stepping in the, I guess, down the slope until you reach what?
Until you reach that the t plus 1 is not different from the t.
Right, or it's like less than, they're either the same or less than.
Yeah, basically that means that this is going to 0, right?
Oh.
And that's why, when we set this equal to 0, that's our sort of
right,
optimal theta.
because ideally this whole thing is all about minimizing the error. So this is your loss function, right? So if you finally are able to make it 0, then you've arrived at your convergence point.
I see. Okay, cool.
And there's a note here about stochastic gradient descent. Use one data point at a time. Yeah, so I guess instead of doing the sum, I don't really understand what this is actually getting at. I guess instead of doing the sum of all the data points, you just use 1. But I don't know how that would be better than. Well, I guess maybe it's more computationally effective, but it seems like it would give you some poor results.
So it's taken the gradient of 1 point, or computing the gradient of just 1 point instead of the entire data set, which kind of like you were hinting at, it would be a lot faster and you'll have to iterate more times. However, it's found sometimes to produce the global minimum more often because it's stochastic, it's random, it's not necessarily going in the correct gradient of the data set. It's just going the gradient of 1 point, which can get you out of some local minima in some cases, depending on if it's not a convex problem.
Okay, that makes sense.
So you just pick random eyes. You're going to go until you converge. You compare it to like another random eye, and then.
I think that's one way to do it, but it's you usually iterate and do each point. So choose one, then choose another, then choose another, and you keep using all of them. Or it doesn't have to necessarily be one. It can just be a sample of the points. So the first equation is for batch gradient descent. You're using all the points, but
Right.
you could just the stochastic or a mini batch or sample. It's just less than all of them.
Yeah, I think we'll talk about this a little bit later too with like lasso regression, and so we'll come back to this, I think. And what is it? It's like it's some way to analyze how your regression went, but we'll talk about it. Okay, so I guess a recap on this. Yeah, so you can do the stochastic gradient descent, pros, online, super low cost per step. Cons, coordinates, maybe slow. What does that mean, coordinates?
You're doing point by point.
Okay, point by point. And maybe slow converging. So you might have to do a few of these to see what the actual point is. Then gradient descent, fast converging, easy to implement. But the cons are you need to like kind of read all the data. I guess that's the difference between the stochastic and the full gradient descent. The normal equations, or the sort of pseudo inverse form, it's a very single shot algorithm, so it's closed form. You just do it, you compute it, and it's done. So easiest to implement, but you have to compute this inverse, so it can be expensive. You can get numerical issues if the matrix is singular, but yeah. Just use PM to avoid some of these, but you can't get away from the computational expensiveness of it. It's just hard to do, especially if you have a lot of features. Okay, linear regression for classification. So here we have some raw inputs of different features, and I think this should be, yeah, so you have, yeah, so and then you have your linear model. So this is for some image that has different, I guess 1 to 255, I guess. Yeah, I'm not sure what this is actually getting at, but
It's a 16 by 16 bit image.
Oh, okay.
So that's 256.
Got it. Okay, got it. And so that's each pixel. Yeah, okay, got it. And so your linear model in this case is trying to fit a parameter to all these features. So some way to do that, it seems like, is to just extract some of the useful information. So instead of trying to fit through all of the pixels, I'm trying to extract some of the features that are actually most useful. And so some of the things that we'll think about are, for these images, like intensity and symmetry. And intensity is defined as summing up all the pixels together and getting that one sort of one data point that describes the intensity of the image. And then symmetry is the negative difference between the flipped version. So if you were to like invert the model or the image, I think, yeah, I don't.
It's talking about like if you were to take the picture of that like the picture of that number 1, what you're doing is like if that pixel value is 255, the inverse of it would just be 0.
Right.
Right. So, and it's taking the negative difference between. You ever see those like negative photos? Like they're the. So that's what it's talking about. The symmetry of it is like the difference in pixel values.
Okay, yeah. So I guess basically the point here is that like you can kind of extract some useful information. And so here they're plotting symmetry against, so x0 is like the bias, so this is just like your 1, right? And then your 2 features that you're actually using is intensity and symmetry. So instead of using all the features, if you just plot these numbers against intensity and symmetry, you'll see that there's some, there's at least some like line that you can kind of draw and separate these two or these data. So the point is you don't need to like go through all the pixels. So just try to get some useful information, and that'll be dependent on the application, but that's kind of the idea. And then for classification, so we just talked about regression, yeah, I guess we just talked about regression, but we'll talk about regression for classification. So for here, we'll just consider two classes, so binary valued functions, and we'll consider those two classes to be plus or minus 1. So you can either have value 1 or value -1. And so you use linear regression where you have some data points, your features and the parameters, and you're going to basically say those are approximately yn, where yn can only be 1 or -1, right? And so basically what we can do is, one way we can do that is just calculate the sign of this regression function, or this prediction function. So you assume that you already have your theta, your parameters. So we can calculate the sign of this linear combination. And if it's greater than 0, I mean, if it's less than 0, you classify as -1. If it's 0, then it's 0. If it's greater than 0, you classify as 1. So this is kind of a schematic of this. So you have all the features here, and you put them into this summation block where you're taking the linear combination of both these thetas and your features, and then those go through some sign block, right? Where they're classified as either 1, -1, or 0. I don't think the 0 is that useful, but I guess in the case that, yeah, because it doesn't really give you either 1 or -1, so I don't really know what you would do when you did 0. But it seems like it's very unlikely that you get 0 anyway. But you basically just take the sign of that, and then that is your output, instead of something that's more granular than that. So yeah, basically what that looks like is you have some data that you collected, and your linear regression model is basically just going to create this line, this split line, and everything above that line is going to be classified as 1, and everything below that line is going to be classified as 0. I mean, a -1. And then if you're on that line, then it's 0. But in that case, you have to throw that thing into one of the bins and see. Yeah, so not really the best for classification, but it's a good start. Okay, so extension to higher order regression. So we talked about linear regression, but what if we want to do polynomial regression, right? We want to fit something that isn't quite linear, or a line wouldn't be the best way to fit it. So what we can do is we can just, instead of having these be x1, x2, and so on, we can just take the x as 1 here, or take this feature here as x, and then square this feature for the second one, and then keep going, and you can raise them to whatever polynomial you want to raise them to. And to make sure that we can still do linear regression, what we'll do is we'll just rewrite these variables. So this x now is going to become z1, x squared is going to become z2, and so on. So this x raised to the d is going to become zd. So we kind of just like rewrite these variables so that we can still do a linear model. You can still fit a linear model, but in the actual computation of it, you'll make sure that you square whatever feature this is before you put it into the linear regression. So yeah, so the way that works is basically the same way. So you still have your mean square error, and you set the gradient to 0 to find the parameters. So same stuff. And now you have your solution is still the pseudo inverse of z times y. And yeah, if we choose a different maximal degree d for the polynomial, the solution would be different. So it's really dependent on what D you choose, like how much you are like sort of raising the X to. I'm not sure what this is trying to say. So yeah, I guess in terms of what is happening, you have some X vector, right? Yeah, so you have some X vector, and what we'll do is that our first feature here, our sort of Z1, which is X, is going to just be that X vector, and then Z2 we're going to take to be X squared. So you can see that this is just this X2 or Z2 is just going to be our X1 squared, and that's the second feature. And then yeah, and then you have some Y's that you have measured, and they're still the same. And then I guess these are the fitted values from that fitted coefficients from the linear regression. Yeah, and so what this looks like in feature space. So if you have I'm not really sure what this is getting at here, actually. Okay, let's read this. We're fitting a d-dimensional hyperplane in d+1 dimension hyperspace. The above example, a 2D plane in a 3D space. The hyperplane is really flat, linear, and 3D. Can be seen as a nonlinear. Oh, I see. Okay. Yeah. So like we're basically So basically by making sure, or by setting this as Z instead of like X squared or something like that, and keeping it linear, we are still creating a linear plane in some like 3-dimensional space or some other d-dimensional space, but now we're fitting on that plane. There's going to be a nonlinear function on that plane. So originally, you can do, if you just have two, or if you just have one feature, you can have a line. And then also when we had more than one feature and we were still doing linear regression, you basically had just a plane. But now we're actually fitting a line or a curve onto that linear plane, is what kind of is happening geometrically. I think that's what we're looking at here. Yeah, so basically mapping this curve onto this new linear plane. So the linear plane, so I guess to kind of summarize, the linear plane is basically your Z times theta, and the curve on that plane is like your one. So Z times theta is plane, and then your curve is your like theta 0 plus theta 1 x plus theta 2 x squared, and so on. Okay.
Can you go back to the definition of Z real quick?
Mm-hmm. So it's just these, because remember we're creating matrices from data that's already measured. So we just take this x that we've measured and we square it. And now this is Z1 and this is Z2.
Where the subscript represents the. Can you go back to the definition of Z? I was trying to understand the dimensionality of this.
Yeah, I think in this case the
So D represents. Well, go ahead.
Yeah, so I think in this case, we're kind of just considering, the notation's a little weird. So like we're kind of considering these as, let me think. So if you have multiple data, yeah, so this is for one feature, right? X. So I'm trying to think about how it would map to multiple features.
Okay. Can you go back to the definition of Z real quick?
Mm-hmm.
I just want to look at it and make sure I understand. So, okay, so D represents the polynomial that we're fitting it to, and where each X represents each, I guess, the feature raised to a different polynomial.
Mm-hmm.
And Z just represents, like, this is just for one, I guess, measurement, if you will.
Mm-hmm.
Or I
Yeah.
guess one measurement, but no, it's not one measurement. It's we're taking one feature in our data set.
Yeah. Let me think about what this would look like for. Yeah, it would get really complex. But you could still write it. But it'd get really complex if you were having like multiple.
What's going on?
I'm just trying to understand the dimensionality of this. Like, looking at Z, where we're taking the feature X raised to a different polynomial up to D, right?
Mm-hmm.
And you probably have multiple measurements of that feature. That's how we are able to do our regression.
What do you mean? What do you mean by multiple measurements of that feature?
I guess I'm imagining a data set where I guess I just don't understand what's happening right now. Are we taking one measurement of one feature and we're doing a linear regression? How this feature correlates with Y to some polynomial D?
Well, yeah, I mean, it's the same thing as in the linear version of regression. The only difference is that you're essentially creating additional features, which are those features being raised to some power, to some polynomial degree. So like if it was just one feature, like Y versus X, and now instead of it being Y versus X, it's Y versus X, X squared, X cubed,
Yeah.
X to the fourth power.
Oh, I see. So we're comparing one feature to one output. And we're essentially making more features by raising it to whatever to
To
up
various powers, yeah. And you can still have more features. It doesn't have to just be one feature. If you have multiple features, for each feature, you're going to now have D versions of that feature.
Okay. So if we scroll down to the equations we're using, those also work for three-dimensional matrices?
Yeah, you just have to write them. You just have to write this properly. So let's say you had two features, x1 and x2. And let's say you were saying that this depended linearly on x1, but it might also depend quadratically on x2. So you had x2 squared or something like that. So instead of having your sort of matrix or whatever just be x equals, and these are vectors, so vector of 1, vector of x1, and vector of x2, you would just add another feature of x2 squared.
Oh, that makes sense. Okay, that's super subtle.
Yeah, I had to think about it for a little bit, but I think Kevin's answer also helped.
Thank you.
Okay. Okay. So then you also have some choices when you're doing this kind of polynomial fitting, right? So you get to choose the degree to which you want to fit this data. So right now, let's just think about this one dimension or one feature. So you have some x data that you're trying to put in a function to get t out, right? This t over here, x, and you have some degree that you get to choose, right? So here we choose that it's just 0, so you get a flat line. And if you choose 1, you get a line, a linear regression. Choose 3, you get some sort of polynomial shape. But then you can kind of do something that is really bad, where you kind of overfit. So you can choose the degree to be 9, such that it goes through each one of these points. But now your data kind of, or your fit, your predictive model doesn't actually match the true value or the sort of estimated value very well at all. So so we want to think about a way that we can increase. Yeah, I guess this is not really that important, but we want to think about a way that we can increase the degree sort of to some level that has a good fit for the training data, a decent fit for the training data. It doesn't overfit the training data such that the test data or the predictions for the test data are useless. So for example, if we had like some test data that was in the middle here, that would say like our prediction would say like, the t is supposed to be so far up, but we actually want it to be, somewhere around here. So the idea is that you kind of do need some way to one, choose the degree reasonably, and you don't want to overfit. And then there are some ways to like make sure that you don't overfit by using regularization in the linear regression. So yeah, so that's it for this one. And
Wait. Oh, okay. Can you go back to the last slide, actually? I think they're saying two different things. Because like one is pick your dimension and evaluate it such that we know it's good enough to actually predict. But then the comment says like we want to make it such that the curve passes through all training points.
No, it's asking, do we want to?
Yeah, because if you look at d equals 3, you would say that's a pretty decent predictor.
Mm-hmm.
But if you look at d equals 9, you overfit in a lot of places. You're
right.
Yeah. So just because you could have a higher degree polynomial doesn't necessarily mean it'll be a better predictor. Right.
And I agree, but I think this comment is a little different than saying like what degree. It's saying can we go through all the points, but then smush our curve such that it still follows it. Does that make sense? Because I think if it was just about minimizing the error, you take 3. But if
I see what you're saying.
Yeah, if it's about like using every single training point, then
right.
Somehow, is it regularization? Is that the concept where you're taking then
Oh, you never really want to use every training point.
you said what?
I said you never really want to use every training point. That's not going to be a good model. So I think this is like a yeah, just like or I guess like a rhetorical question to get you to think about this. I don't, and I also don't understand what you mean by smush.
Well,
I think I understand what Stu's saying. It's like if you look at d equals 9, if you continually increased the polynomial degree, you would likely have higher and higher amplitude like curves. You'd have higher order curves. And so it's likely that you could have a curve or some polynomial that will hit every training point. But you'll have a really high variance like between points. And so he was suggesting, does regularization mean there's a way for you to flatten that curve?
Yeah.
To reduce the peaks and the troughs so that you still get a curve that goes through all the points. That's a higher order degree polynomial, but without that variance.
Right.
Okay, so yeah, I mean, generally, yeah, that's what regularization is going to do. But I think that the idea of passing through all the training points is actually not what you want to do.
Yeah,
in my experience.
Yeah, it leads to overfitting quite often. So it's not actually that beneficial. You do actually want to leave some sort of gaps, I guess, so that your model could be more general.
I guess I just wonder if the rules change when you have massive data sets. Kevin, you there?
So
Okay, can you help us with the slide real quick? So, I guess we're having a bit of a debate, because like it looks like there's a couple takeaways from here. One is like, we probably need some way to evaluate the maximum dimension we want to use when fitting for regression. But then we're looking at this comment that says, can we increase the maximal polynomial degree to very large so that it passes through all the training points? And so our question, because like typically we don't, I guess the convention is don't go through all the training points, leave some error like D3, and that's a better predictor. But is there a concept in machine learning where you do need to go through every single point?
you do need to go through every single point. Um, um, I think theoretically, I mean, if all the points were on the proper polynomial function, then it would be fine to go through all of them. But I don't know. I don't really usually think about it like that. The point of this slide is that if you in theory can hit every point, but you're going to get massive overfitting. So this is leading to the concept of regularization, where you essentially don't make that an option. Because and they have some, I don't know, I think that's in the next lecture, on the regularization lecture, they have some, like, they help you build some geometrical intuition. Like if you assume the function's a circle, you don't want the loss function to go to 0, which would be a circle of radius 0 or something like that. But yeah, so the point is you don't want the function, the error, to go to 0, which will not allow you to hit every point.
Okay, I see.
Does that make sense?
Yeah. No, sir. Are you doing regularization today?
Yeah.
Oh, okay. I'll just wait then. Okay, thank you.
All right, let's move on. Okay.
Should Should we do one big lecture, or do we break the recordings up?
Oh.
So I'm gonna grab water real quick. I'll be right back.